Okay, all right. Let's get started. Okay, so today, as I said, right, like we would be looking at what are all the sequential circuits and what it is actually, and how do we design that and all of that. Okay, okay. So whatever we have seen in the last class and prior to that was mainly the combinational circuits and how we use them and why it is very important to optimize those circuits and what are the basic building blocks and etc. Okay, and today we will be looking at the sequential circuit, which is more and more important. It's basically without sequential circuits you will not see any kind of design in the industry. Okay, okay, what is sequential circuit? So if you look at, right, the combinational circuits, they will just remember only, the output depends on only the present state. Okay, but whereas in sequential circuits it is kind of, we call it as a kind of combinational circuit plus a storage element. Okay, and output depends not just only on present inputs but on the past sequence of inputs as well. Okay, so now what is this meaning? So it is basically a kind of, your inputs and then your past state, and depending on that also your output gets changed. Okay, now what are the basic sequential elements that we might see in our designs? So in your textbooks you will see only kind of, say a latch and then flip flop, but when it comes to industry you will again see macros. Okay, I would be explaining you what it is. Say you have a memories, say you have a SRAM, and you have a ROM, read only memory, and then there are different types in that itself is okay. So macros meaning, say for example memories, and then say CPU or say GPU. Okay, and all of that. And so let's understand the basic sequential elements, then we would be able to understand the bigger elements, and and so on. So what is latch? So latch is basically a level sensitive. Okay, I'll explain you what is level sensitive and what is edge triggered and as well. So flip flop is an edge triggered. Okay, now remember, for combinational circuits there is nothing called controlling signal, but whereas when it comes to sequential circuits you have something called clock. Okay, that is one of the important signal to control your whole circuit. Okay, now the clock signal, right? So based on this clock signal only these circuits will switch us. Now let's say you have got a clock. Okay, so clock would be say something like this. Okay, now when you say a latch, right, then the level sensitive, that means it is basically, it is a positive level sensitive. That means during this whole period the data can get passed. Okay, whereas when it comes to edge trigger, so only during the rising edge, so it is called positive edge triggered. Okay, or if there is a flop which triggers during the falling edge trigger, then it is, we call it as a negative edge triggered. Okay, so your flops will capture the data from the input to output during the edges only, whereas latches will capture during the whole pulse. Okay, so this is kind of, we call it as a positive level sensitive, and this kind of, see, if there is something which is captures when when the clock is at zero, right, then it is negative level sensitive. Okay, okay, so let's understand more on this. So when you look at a clock, okay, so your clock will have different characteristics. Okay, say what does this meaning? It's basically, so when we say a clock, right? So we actually, now remember, when you draw a clock, it is always good if you draw it like this. So I know in your textbooks you may have it like this, and when we draw in any kind of interviews and everything, probably people usually draw like this. But remember, this is a kind of ideal scenario which is not going to be true all the time. Whereas this is how I usually draw it. Okay. So now in this, if you look at, say the whole thing is here, right? Now this is one cycle. Okay. One cycle. Now, if you look at here, say here from here to here, so this is your rise time or rise transition. Okay, rise time or rise transition. Okay, and when you look at this particular thing, this is basically fall time. Okay, or fall transition. Okay, now people even call this also as a clock period. So people usually say T clock. Your clock period is kind of say 2ns, okay, or even say 1ns, depending on the design requirements, okay. And your frequency, so remember, this is one of the important problem that you will get in interviews. So it's basically, now what is the formula? So basically F equal to 1 by T. Okay, this formula I'm sure everyone knows. Now, when you go and calculate frequency, so basically say I have given you 2ns. Now, what would be your clock period? I mean, the clock frequency, anyone? 1 by 2ns. Now, what would be the frequency?
0.5 gigahertz.
Sorry?
0.5 gigahertz.
Okay. What about others?
5 gigahertz.
Okay. So the first answer is point 0.5 gig, and the second answer is 5 gig. Okay. Next, unmute and talk. Well, it's a kind of interactive session.
0.5 gigahertz.
Okay, so two votes for that.
I think it's
500 megahertz.
500 gigahertz.
There is one more answer, 500 megahertz. Okay, okay,
It's 500 gigahertz.
okay. So 500 gigahertz.
500 to 10 to the power of 9.
No, I just need a final answer.
Yeah, it's
Okay,
500 gigahertz.
okay, perfect. Anyone else? We have 20 plus people. I have hardly got 5 6 guys who are doing the work.
0.5 gigahertz.
Okay, so till now, this has got two or I think three votes, and this is
Point five,
kind
point
point.
0.5 gigahertz. Point 0.5
Okay,
gigahertz.
okay. So there is one more here. What about others?
Both sir 0.5 gigahertz at 500 megahertz.
Okay, you are the one who said 5 gigahertz. No.
Pres- Just now I analyzed the 0.5 gigahertz and 500 both.
Okay.
That's the giga.
Actually, I said that 500 megahertz at the same time. So it was same.
No, no, I understand that, that I think Shruti said 5 gigahertz. Yeah. Okay. So ideally speaking, this and this are same, one and same. Now, someone said 500 gigahertz, and I'm just still waiting for others to answer. I'll wait for 1 more minute before I start solving this.
500 megahertz.
Okay. Plus one. Next. Don't follow the crowd. There is no guarantee that crowd is always correct, and I might pull you to answer how did you solve it as well. So follow your answer even if it is wrong. Okay, maybe the others are not putting effort to solve it. How should I take it? Guys, I need you to be active in the class and start solving the problems that I give you in the class. Okay, so now, so when you say 1 ns, what is it? It is exactly, or say 1 microseconds and 1 milliseconds. So now this is going to be 10 to the power minus 3.
3,
This
10 to
is
the power
going to be,
minus 6, 10 to the
minus
power
6,
minus 9, minus 9,
minus 9.
minus
yeah,
9, yeah.
1 ps meaning
10 to the power minus 12.
minus 12.
Minus
Okay.
12.
Okay. Now, so this is in terms of your seconds. Now, when it comes to the megahertz, right? So 1k is equal to 10 to the power 3, and 1 m equal to 10 to the
10 to the
power
power 6.
6,
Or
and 1 gig is equal to
10 raised to 9.
9, and 1 t
10 raised
is
to 12.
equal 10 to the power of 12. Okay, now a simple math, 1 by 2 into 10 to the power minus 9.
Minus 9.
Okay, now when you solve this
0.5 to
math,
10 to the
so
power of 9.
it is 1 by 2. This minus 9 becomes,
Plus 9.
goes into
10
the
to the
top.
power of plus 9.
This, it becomes 10 to the power 9, and then this becomes 0.5 gigahertz, and which is equivalent to
500 megahertz.
500
Megahertz.
megahertz. Okay, so the right answer is, as I said, this is the right answer. So remember, this solving is definitely would be asked in at least in each and every interview. So I at least know, okay, this person is how good is in the mathematics, at least a basic mathematics. Okay, I what I do is I just give them a problem of timing and ask them to calculate the max frequency, what is that circuit that can operate, and eventually you will end up with doing this kind of calculation. Okay, so let's see some more problem. Okay, now if you look at this 100 gig, that means it is basically 0.01 ns. Now 10 gig is basically zero point 0.1 ns, and 1 gig is basically 1 ns, and 100 megahertz is 10 ns. Now 10 megahertz is 100 ns. Now, you know what? Sometimes I have design operating at 900 megahertz. What would be my clock period? Sometimes, my actual designs, some of my designs were operating at 900 megahertz. Now, what would be my clock period?
90 nanoseconds.
19 megahertz.
90 nanoseconds. Okay. What about others?
90 nanos.
Okay.
90 nanoseconds.
Okay. How do you guys come up with this 90 nanosecond?
900 microsecond.
1.1.
900 microseconds. What is happening? I think something is going wrong here.
It's 0.01
That's
10
Point,
nanosecond.
1.1 nanoseconds.
Point
Go ahead with your answers. Point 1.
0.01 nanoseconds. Wait.
0.01 is 100 gigahertz, no? I'm just giving you 900 megahertz.
900 megahertz. Okay. 900 power to 6. 9 into 10 to the power of 9. 1 by 9 is 0. 10 to the power of. Is it 9 nanoseconds? 0.1 nanoseconds.
You have 10 gigahertz. You have the table on the right side. You see this?
Yeah, point. It's 900 megahertz. 100 is.
that's 1 nanosecond.
So 900 megahertz. Okay. So it is.
I don't
90
know. So
nanoseconds.
there is, if you guys were in my position, I gave one problem, and you guys are playing with my and with me it's the different answers. Now choose whatever best you want. Okay.
9 seconds. I will find out. Which is.
This makes me scared. Should I give any more problems? If you guys don't want to solve problems, okay, that is fine. But
One.
not this much. Sorry, go ahead. Madan, you are saying something?
One.
One
1.1 nanoseconds.
Okay, so there are two
1.1
people
nanoseconds.
has given this. Okay, so Jai Surya is giving one more on this, 1.1.
It's 1.1 nanoseconds.
Okay,
0.01. 0.01
That's what I
nanoseconds.
said. 0.01. I said.
1 nanosecond, sir.
okay,
So 90
so,
nanoseconds.
okay. Okay, 900 megahertz. So let's just try to solve it. So it is your T is basically 1 by F, which is basically 1 by 900 into 10 to the power 6. Okay, now this 1 by zero point 0.9 into 10 to the power. Okay, let's do this way. So let this be there as it is. 1 by 900 into 10 to the power minus 6 when it goes on the top. So now 1 divided by 900 is going to be, so this is microseconds. Now if you do this in the calculator, it is basically coming like 0.00111 into 10 to the
Into 10 to the
power
power of minus 6.
6. So now when you take this actually three more, basically this three things, you take it, so then it is going to be 1.11 into 10 to the power minus 9, which is basically
1.1
1.11 n.
nanoseconds.
Yes. Okay, what punishment we should give to all the non-correct guys? Basic mathematics. So you should solve some more problems. Okay, so 633 megahertz. Okay, 633 megahertz. What would be your 633 megahertz? What would be your clock period?
1 second, sir.
Yes. I see some of the people are completely quiet.
nanoseconds.
1 point?
1.5 nanoseconds.
1.579 nanosecond.
Okay. So 1.5. Okay, I'm just keeping it approximately 1.5. Maybe one more digit. What would be the next one? 1.5.
1.757.
8.
7 man.
Okay, 1.57 ns.
7.
Okay. Okay, so it is going to be 579, meaning you can take it like kind of 5.8. Yeah. Okay. Now, this, right, if you look at it, 1.58 nanoseconds, the reason why I'm bringing up all this is these were all my different clock frequencies of my designs. Okay. So there is nothing called round off here. It is all depending on your requirements and what is that they have and all of that. Hmm. Okay. Now, see, remember the way I always remember or try to keep it right, because I keep interviewing people on almost daily basis. So it is like this. So when someone says 1 ns, so it is kind of 1 gig. Okay. When someone says 2 ns, it is kind of 500 m. Now anyone says between 500 and 1 gig, it is always between 1 and 2 ns. So that is how I always remember. Okay. So it is going to be kind of easy if you know that. Okay, yeah, so you will see this kind of questions coming in your written tests as well. Definitely, because this is nothing to do with your STA or any of this. So this is just a basic, a simple formula which you might have gone through in your you know engineering. So now the reason why I'm telling you this is, so if you look at some of the uh, projects that are probably the designs, say for example Snapdragon. You see here, there is a 3.7 gigahertz. Okay, now what would be your period here? 3.7 gigahertz. What would be your clock period here? Approximately.
0.27 nanoseconds.
Okay. So you're saying it is basically 270 PS.
Yeah.
Okay. What about others?
It is 270 nanoseconds, sir.
Nanoseconds?
Yeah.
Okay. What about others?
No,
Let's wait.
3 point.
I'll
Yes,
have my time to beat.
1 second, 1 second. One. This 0.27 to 10 to the power 6.
0.27.
That is it is 270 nanoseconds.
270?
Nanoseconds.
Okay.
else 0.27 microseconds.
Okay. So now there are two answers. One is 270 PS and there is a 270 NS. Now you both fight and come up with the right answers, please. You guys decide. I kind of I'll have to go and take
270 PS.
Okay. So there is
270
a
PS.
okay.
0.27 nanoseconds.
Okay, 0.27 nanoseconds, which is eventually turning out to be 270 PS. Okay. There are a lot of people who are quiet.
270 PS, sir.
What, sir?
Okay.
270 picosecond.
Okay.
PS. I have taken as 10.6, so it is 270 PS.
Two 60 picoseconds.
Okay.
Minus 9. It's 270 picoseconds, sir. Okay.
Okay. So yeah.
270 picoseconds.
Okay. The reason is now okay. So when we talk about the frequency, right? So is it easy to work or easy to close 500 megahertz design or 2 gig and above, which is easy to close?
5 megahertz.
100 megahertz, sir.
400 megahertz.
That is 2 gigahertz.
Okay. So just remember this question. Keep it noted side by. Okay. We will revisit this question probably after a couple of classes. Then you would know your exact answer. Okay. Okay. Let's move on. Okay. So the first thing here is it is basically okay. Let's do this first normal problem. Then we will come here. Okay. So for example, the first thing is flip flop. Okay. So this is your pulse, clock pulse. Now, and then say this is your D. Now, what would be your, output? Okay. Now, as I told you, right, this flops is known as edge trigger. So, and this is assuming this is your positive edge trigger. Now, remember always I put this way. So this is how your flop edge triggered is depicted, or probably we show it in the any of the block diagram and other things. So it is something like this. So now you have just drawn it like this. Now say your Q. Okay. Now what is this value here? It is 0. Okay. This 0 would continue till your next clock pulse. Now here 1. Now from here it will continue till the
Yes, one, one.
next clock pulse. So next is again 1. It would continue till here, and then it would actually go down. So what is the secret here, or probably how do you do this? So just mark the edge, and exactly look at your D near that place, and then mark that, so logic 0 here, go all the way till next edge. Now remember, though the data is changing, okay, but do you see the output is kind of changing? No, because it
No.
is a kind of storing the value. So it is whatever during this edge, that value is retained till your next clock pulse arrival. Okay, now here if you look at, so there is a next pulse, and here it is a logic 1, and you see here logic 1, and it goes all the way till your next pulse, leaving any changes in the inputs, not at all considering it. So it's something like gate. The gate opens every certain minutes. Say for example, say this is a kind of 2ns period. Okay, so the gate opens once every 2ns. Okay, and so it's just that, letting people go. So that is exactly what it is. So now this is how your flip-flop actually behaves. Now when it comes to a latch, okay, when it comes to a latch, let me just take a snapshot and put it in the group. Okay, now let's go back and do it for the latch. Now this is going to be Q latch. So for latch, we always just say, see, some people have EN pin or CK pin. Okay, so this is going to be your D, and say this is going to be your Q. Okay, and this will not have this edge trigger shape. Okay, now remember what is the latch form, how the latch operates. So this is positive latch. Now during this, so whatever is there here, it is exactly copied over here. Okay, and then exactly whatever during the active edge, you just have to copy it exactly the same. And then this is kind of, see, this, and so this is kind of, see, low. Now you just have to connect this, okay, and till this edge, and then connect it. Now this is how I draw it for the latch. Okay, so this is your active period. Okay, so as I told, say for example, now this is your active period, whatever is the shape that gets exactly captured here, and the same case here, this is a kind of active period, this gets exactly copied over here. Okay, so that is how your latch basically operates. Okay. Any question here?
Sir, could you please repeat this once?
Okay. So what is latch? So it is basically positive latch, meaning during this positive pulse, okay, or during this pulse, now it allows the data to travel. Okay. Now anything that is, it's kind of you keeping the door open for 1ns. So total you're having a 2ns is the period. So you have keeping 1ns as a open, you're letting the people pass through, and you're closing the door for 1ns. So now that means the data, basically the D, whatever is there in the D, it gets captured to Q. Okay. And flop, there is no D to Q direct path. There is no path D to Q. It is always kind of clock to Q. Based on the clock edge only, it would be there. We'll talk about something called timing arc in the upcoming classes. Okay. So latch meaning, positive latch meaning during this positive thing, it exactly kind of copies over here. And during the negative, it is just kind of retains its state. It just retains its states. There is, see here, the data is changing, but it is basically kind of retained. Okay. So here also the data is changing, but it is kind of retained.
Okay, sir.
Okay. So I'll give you one more. So this is always kind of say CK pin. Okay. So sometimes people call this as an enable pin, or kind of CK pin as well. So it depends on the library. So you will get to learn in the upcoming classes. Okay, now let's get back to our problem. Yeah, can I guys try solving this? So remember, this is positive latch. Okay, you don't see the uh, trigger here. So this is ideally, it is a kind of latch. This is positive flip-flop, positive triggered flop. And this is again flip-flop with negage. Okay. I'll be back in a minute. I'll just take some water and be back. Done. Am I audible?
Yes, sir.
Okay. So let's go one by one. So what did we discuss for latch? So whatever is there during this age, it is exactly going to be copied. So from here to here, it would be exactly copied. Now you see here. Hold on, what is happening? It is a D latch. Okay, Q A. Yeah, okay. So it is basically going from here. So it is exactly getting copied to the output, and then it is kind of stopped over here. Now the whole negative pulse, it is kind of the last value is retained, and again here it is kind of copied. Whatever is there at the input, it just copied, and then it would be kind of continued whatever the last state. So is there any clear query here on the latch part? Okay. Now The next one is your QB. Now, what is this? This is basically a positive edge triggered flop, and whatever is there on the edge, the value of D, so it is high. So it is kind of marking it as a high all the way till your next edge. Now here it is kind of low. So bring it to low and then continue all the way till your next edge. Okay. So this is how it is actually going to be. The output is going to be something like this. Okay. And we'll wait. Is that clear? Any questions? Okay. And the last one, it is basically negative edge triggered flip flop. Okay. And remember, you sometimes people say, Kumar, can I just invert it here? So instead of Q, if I add one inverter, isn't it going to be the same? No, the answer is definitely no, because when you say negative edge triggered, it is actually going to capture the value which is at the falling edge. Okay. So you cannot do just the inversion of this particular the previous one and say that is kind of negation circuit. Okay, so here continuing in the low, and here it is again low, continued all the way till your next falling edge, and here it is high, and we just take it to higher side and be done with that. So that is how your flop versus latch, and this is something that we call it as a kind of the waveform, or probably sometimes people even call it as a kind of the diagrams, the timing diagram kind of things. Okay, so I usually say the output of latch and flop. So people call it with a different names. So you just need to understand the concept, basic concepts. Okay. Questions any here? If you have anything, you can just ask before we move to the next one. Okay, moving on. Okay, now the what are the different flops that you are aware of? What are the different flops that you are aware of? So it is basically we have four different flops. So if you look at one is SR flop, okay, and next is JK flop, okay, and then we also have something called D flop, and then the last one is called T flop. So now, which is the one we use in industry predominantly? So remember, we always use only D flops. So you will see DFFs being used in the design heavily. Okay. So your homework. So what is SDFF? What is SDFF and what is the main? Okay, SDFF versus DFF. So try to find the difference and what is the difference and in terms of circuit, in terms of area, size, and everything. Okay, so we always use only the D flop. We don't use any other flops. Okay, so you don't need to really go and look at, okay, what is this JK flop, what is the meaning of storage, storage state, and then toggle state and all of that. So you don't need to worry about all that. Okay. Now, what is this excitation table? So why this excitation table is important? Why this excitation table is important? So remember, as we discussed, sometimes you know what is your present state, okay? What is your present state and what is the state that you want next state, and now you would need to give certain inputs, next inputs. Okay, so depending on present state and next state, you would actually have to choose the inputs. Now this excitation table would actually helps you to find, looking at present state and next state, what should be your inputs. Now you design your system accordingly. Now say this is your present state and you want your next state to be say 0 to 0. Now your the next input that you should give is 0. Now let's say your present state is 0 and your next state is you wanted to be 1. Now the input that you should give or supply is 1. Okay, now again your present state is 1 and your next state you want it to be 0, then you need to give 0. Now let's say you have your current state is 1 and next state is again you're looking to keep it as a 1, and this your next state also supposed to be 1. So now, I mean, the input should be 1 now. So your system that you need to design is based on these values. Okay, now I will also show you a simple counter designs where you would make use of this excitation table. Okay, so this excitation table is one of the important uh, what do you call reference point where you would actually have to know what is the current state, and if you have next state of certain things, and this is what your input should be. So without this you cannot design your say for example counters and then FSMs and all of that. Okay, okay, now moving on to the next topic. So what we will do is, so we will try to cover this registers, shift registers, and then we will take a break. Okay, I hope you guys are okay with that. Or do you guys want to have a break now?
No, sir. We'll finish up this and we'll have.
Okay, all right. So shift registers. Okay, so simple, right? What is a register?
Storage element. To store data.
Exactly. So registers are, normal flip flop. Also, we call it as a registers. Okay, and it is basically a storage element. Okay, it stores values and it can be used to shift. Let's say you wanted to, say right shift, left shifts, and etc. So it is kind of can be used as a shift registers. So it's basically a storage element. Okay, now shift registers. Now before we go in there, right? Now what is this? It's basically a 4-bit registers. Now just understand this circuit. So these are all made up of the D flops. Okay, and there is a common clock signal that is driving all these 4 flops, and then this is the kind of input signals which are kind of loading the data. So yesterday I was talking about designing an ALU, right? So your data at certain point it would be kind of connected to this D, and the moment you pass a clock, that data is kind of captured to queue, and then your q1, q2, q3, q0, these are all kind of becomes kind of constant. Now, I mean, a constant in the sense the value gets stored, so they don't change till your next clock comes into picture. Okay, so this is kind of used to store the value, and it is the output is not going to, it is kind of, memorized, so it could be used during your, operations or, processing, data processing and all of that. Okay, so now this particular register, it is basically parallel in and then parallel out. Okay, it is basically loading everything in parallel and sending it out in parallel with one pulse. Okay, now let's understand a little more on the registers itself. So there are different registers. So one that is very famous is basically it's called shift registers. So now shift registers meaning what? It's basically group of flops connected in a chain fashion. Okay, now output from one flip-flop becomes the input to the next flip-flop. Now if you look at this, what kind of register it is, what kind of shift register it is?
It is serial in. Serial out.
What about others?
Serial in, serial out.
Yes, sir. Yes, sir. Yes, sir.
It is basically serial in, serial out. Okay, so data input and then passing all the things one by one. Now and then after certain pulse, you will get the data out. Okay, now you just have to remember, it might look very simple and it is of no use, but remember this kind of shift registers you will see in our designs a lot. Every designs will have. So people, I know some of you are already working in industry. So remember, you have something called a scan chain in our designs, the DFT scan stitching. The scan chains are basically shift registers. Okay, so we would discuss more on the scan chains and how the shift registers are, the form of shift registers. So we talked about something called the SDFF, right? I just gave you a homework, right? It is basically a scannable D flip flop. And in your flop, you will have the pins of, say, CK, D, and then Q, and then say set, and then reset. But in SDFF, D, say SI, and then you will have something called SE, scan enable, and then your clock, okay, and then your reset, and then your Q, and then your set. Okay, now remember the all the designs, okay, all the flops present in the designs, right? They would be kind of, there would be two parts. So one is Q2D and then Q2SI. Okay, Q2D and Q2SI. So remember Q2D. Q2D is always known as a functional path. Functional path. Okay. And Q2SI is always a scan path. Okay. So the shift register is basically Q2SI. It is all the anything that you see with the Q2SI, it is, we call it as a scan path, and that is basically our scan chain. Okay, so it is basically your input. You just keep pushing, shifting the data to check if there is a circuit which is working actually fine or not. Okay, so that is your shift registers. Okay, so now if you look at here, what are the different registers that you would have? So one is basically serial in, serial out, and then parallel in, serial out. Okay, so all the things get loaded in parallel but shifting one by one. okay, and then serial in, parallel out, and then parallel in, parallel out. So there are four different shift registers that is possible, and then you also have something called universal shift registers, which could act based on the control. So it can do any of this work based on the control. Okay, any questions here? Shift registers. Any questions?
Give an example of universal shift register.
Okay, so now say, okay, give me a minute, let me just do this. Say for example, now you have a system like this. Okay, so you have kind of all your data that is kind of loaded. Okay, say kind of I3, I2, I1, and I0. Okay, so now you have something like Q3, okay, Q2, Q1, and then Q0. Okay, and then so you have your control 0, and then your control 1. Okay, now say you also have just one, or say you can even keep it like, say, just say Q. Now for example, when control, this both are 0 0, okay, then shift right, okay, now 0 1, shift left, and 1 0, it is kind of serial in, serial out. Okay, so something like this. Now universal shift register, it is basically you have a system now, so you have your control inputs. Based on that, the operations would be carried. Okay,
Okay.
see this kind of registers, right? So sometimes if they have to change the design, dynamically. Okay, so people use this. I have seen people using this in couple of, say, mainly on the interface side, what data they wanted to pass, where they wanted to pass it serially, where they wanted to pass it quickly, depending on the throughput requirements and all of that. So I have seen this in couple of blocks that I have worked in the past. Okay,
So mainly transmitter and receiver.
kind of
Similar.
rules. Yes, exactly.
Okay. Okay.
Okay. Yeah. Okay. All right. So what we will do is we'll take a short break, and then once we come back, we will look at counters. Okay, and then we will also quickly, have a discussion on the FSMs. FSM, I won't be getting into too much detail, because it is not at all needed for PD engineers, but you just knowing it, what is FSM and how it is being designed, is makes sense. Okay, so we'll take a short break and then we'll come and discuss on the counter. So it is 8:16. So let's meet at 8:25. Okay. Okay. So the next topic is counters. Uh, Remember, counters acts, they can just simple clocks, as a simple clocks to keep track of time. And then you'll see the circuit. See, it is end of the day, right? If you look at, say, this is a flop. Okay, now say there is a flaw. Now between these two, some kind of logic. Okay, it can be any logic. Okay, so that is how people actually look at it in the industry. So nobody would even know that this is actually a counter, or this is actually a shift registers and etc. So it is basically they always look at some kind of logic. So this is how we call it as a rich to rich path. So this, when it comes to STA, so we look at rich to rich as one of the path which we would discuss in detail in the upcoming classes. Now coming back to the counter, the circuit actually takes the whole inputs and goes through the defined states, and then it acts as per your the spec. Okay, now let's quickly design a say modulo 8 counter. Okay, now so we will just there are different counters. Okay, so synchronous counter, asynchronous counters, and decade counter, ring counter, Johnson counter, and all of that. Say, but what we will do is let's try to design a small counter, and then we will actually move to the next topic, so that like you understand how it is being designed. Okay, so I would just pick Excel sheet. So now what we are going to do is say mod 8. Okay, counter that we are going to design now. Now say here there is something like kind of Q3, or say I think Q2. 3 flops is what we need. So Q1 and then Q0. Okay, so this is your present state. Okay, this is your present state. And this is going to be your next state. Okay, so I would just say there's a Q2 plus 1. Okay, I just say this as a plus 1, say this as a plus 1, and this is going to be kind of say this is T2, and then this is T1, and then T0. So this is going to be your inputs. Okay, now so we know present state, so 0. Okay, so now you have got this. Now when your counter is at 0, 0, 0, I mean basically at 0, now when the moment you get a pulse, what is the next thing that you get? Your counter has to move to next is kind of 1. Okay, so when it is in 1, the next state it is kind of say 2. Now here it is 2 and it is going to go to 3. Now assuming your counter is in say 7, the output is kind of say 7. Now what would be your next state? It has to be reset to 0. Okay, okay, now let's just keep. Now how do you know what would be your next T or T0 or whatever it is? Now how do you fill these inputs? What would be your next input so that you get this state? Now how do we do this? So this is the time where you need to refer your excitation table. So we talked about the excitation table just some time back, right? Okay, this excitation table. Now, so T. So if you want 0, basically your current state is 0 and your next state is 0. So then you have to keep it as a 0. Okay. Okay. Now say here 0 and here also 0. So it is going to be kind of say 0. Now here also 0. Now 0 and then 0. So that is fine. 0. Now here 0 and 1. Now what is it you need? You need 1. Okay, and one, and so these three are 1 1 1 now, so you need to keep this as a 0. Okay, 0. Now 1 and then 0. Okay, now this is going to be say 1. Okay, so similarly you have to fill for each and everything. Now between, look at this q1 and this q1, it is kind of say 0. Now so 0 and 1, it is 1. Okay, now 1 and 1, it is kind of 0. So 1 and 0, it is kind of 1. So it is going to be kind of 0 1 0 1. Okay, now what about this last one, 0? This, these two things, 0 1 1 0. So it is kind of, everything is kind of switching. So now, so what is it you need to do here? You need to just say fill 1 1 1. Okay, so now you have actually filled what is supposed to be your next input. Okay, now how do you solve this? Now we have got a truth table. Okay, now how do you solve this? Remember we did yesterday Karnaugh map. So use Karnaugh map to solve and come up with the circuit. Okay, can we quickly solve this? So your first flop, okay, say for example this is your first flop. Okay, say this is your next flop, and say this is your the last flop. Say this is, we are designing a synchronous counter. Okay, we are synchronous is what we use in industry, we don't use any kind of asynchronous. Okay, now so the first flop, so this is kind of t0, so you always connect it to 1. Okay, now what about your t1? Can you guys tell me what is solve? You solve this using K-map and tell me what it is. Now to use K-map, you are supposed to use Q3. So Q2, Q1, or say probably Q2, Q1, and Q0. Okay, now so this is going to be 0 1 3 2 4 5 7 6. Okay, now here what and all we have? So 1 3 5 7 1 3 5. Sorry, my bad, I think it is going to be 3, and yeah, so yeah, this is bad, so it is kind of 2. Okay, yeah. Now when you group this, what is that you get? What is this you get?
Q2.
Q1 Q0 bar bar. and then Q1, Q0. So it is, what is this going to be? So this is Q2 bar and this is Q2. So this is going to be Q1 and Q0, Q1 and Q0. What is the values going to be? Let me just pull up the
Q0.
previous. Okay, so 0, 1. Okay, so it is going to be bar, and then so it is going to be like this. Okay, yeah. So now what would be the value here? So your T1, what it is going to be when you group
Q0.
this?
Q0.
So
Q0.
it is going to be Q0. Okay, so now your Q0 is directly connected to your T1. Okay, now what about your T2?
Q1, Q0.
Okay, so your T2 is going to be Q1.
Q0.
You mean and? This is the kind of and, right?
Yes, sir.
Okay, and what about your reset? So here it automatically gets resetted. That's not an issue. But if normally what we usually do is we should also have a reset controller, kind of. See, always it is a negative reset. Okay. So when it is all of them are one, okay, you get reset. So that means all the resets are basically connected to. So assuming it is like not negative reset, or so now Q0, Q1 and Q2. Now this is going to be a reset activator. Okay. So this is how we actually design any kind of counter. So now the first thing that you need to understand here is what is your present state and what is your next state from one state to another. Okay. And then your the inputs. Now this is where I was just stressing little on the K-map kind of things, where it would actually help you to solve some things like this quickly and then come up with something like this. Now remember here what flop that we used. We used T flip flop. Okay, for our learning purpose we just used T flip flop, but remember when you get into industry you will only see the whole design. When you take a look at it, you will see only SDFFs and DFF. Okay, and D latch. Okay, only SDFF, DFF, and then D latch you will see. Okay, so is there any question on the counters?
Yes, sir.
Yeah, hi.
Counter is it a macro or standards?
Sorry.
Is it a macro or
No,
counter?
normal design. No, normal. Just see, it is not a macro. So macros are, we usually call it as a kind of the memories or other bigger circuits. So counter and all is very small. See, you see hardly 3 4 flops, and then you hardly see 2 3 gates. So now putting all this as a macro is something. Eventually, if you really wanted to do this as a macro, you can do it. But I don't prefer doing something like this. Converting a counter into a macro.
Okay.
Okay. it would become very inefficient. Okay. Okay, let me just take a snapshot and put it across.
This reset is NAND, right?
Yeah, that's what I was just thinking. I was not really sure, so I was just thinking. I think it's NAND. It should be NAND when it is negative reset. Yeah.
Yeah.
Okay, moving on. Okay, so your homework is this is your homework. I'll share this in the group. You guys can just try working on it. So they're all not a big deal, but it's just a simple thing. Okay, and FSMs. Okay, so what is this FSM? So it's basically a state machine. It is a digital device that traverses through a predetermined sequence of states. Now, if you look at here, so this is actually basically a counter. What is it actually doing? So zero is your starting stage, and then after certain conditions, it goes to next stage or state, and then from there it goes to next state, so and so on. So this FSM, this particular picture, right, we call it as a finite state machines. And remember, the FSM based designs are heavily used in our designs. Okay, so definitely you and me won't even know, including me actually. Okay, so we don't, because they may have a different states which not simple to know at our level, but they might be kind of having a lot of time, and they spent an expertise and the on the design side, so they would, by looking at it, they would know, okay, how to write a Verilog code for an FSM and all of that. Okay, but what we are going to learn here is just to understand what is an FSM, what are the different types, and that's it. So that is the scope at, here. If you really wanted to understand this FSM in detail, I would suggest you to go through a book called Morris Mano. So that is a book that I always suggest you. So it is Digital Design. Okay, Digital Design book by Morris Mano. Okay, so this is the book that I read. I for during my college, and then there is some author named, I think, Fletcher or Floyd. I'm not sure. So, but I did go through at least minimum 10 plus books to become, good in digital before I get into industry. So, yeah. Now, to be honest, if you ask me, I don't remember many things, but yeah. Okay, moving on. So, if you look at, right, so your inputs and states, your next state decode and output decode, and what is a memory and etc. So, that is how your FSMs are designed. And there are two types. One is Moore machine, and another one is Mealy machine. Okay, so that is the type that we usually have. Okay, and now what is Mealy? What is Mealy? So remember, the Mealy, it's basically, when we say Mealy, the outputs depends on both present inputs and present states. Okay, now if you remember, right, on the state there is no output is given. Okay, it is only when it is traveling from one state to another state, the output would be kind of, you will see an output. Now this is something Mealy state machine. Okay. And coming to Moore, you would see, say here, what is the difference between these two? It is here during the switch, it is kind of, giving the output. Whereas in this case, okay, you see, when it is in the state, it gives you kind of, output. So that means output depends only on the present state. Okay. So whereas, Mealy meaning output depends on both present input and present state. Okay. Whereas Moore is just depends only on the present state. So that is the main difference. So don't ask me which one is good and all. I am not into a design, so I cannot really comment on it. Whatever the real, my expertise is, that is more of PD. But whereas, I don't really have much idea on this FSMs at this point of time. Okay. So I think that's all I wanted to cover on the digital fundamentals. Any questions? So before we wind up this topic,
Only the last slide. This flow diagram. Anyone can you explain with the, for example, A by 0 in Moore and A by 0 in Mealy?
I will have to go through the designs, Abhinay. Maybe I'll try to find some time, and then next week, if I explain, is that okay?
Yeah, fine.
Okay, I'll try. Definitely, I'll try to check that, and I'll revert back. Okay, so maybe a simple thing, right? We can see there are a lot of more, the FSM based implementations that we know. For example, one is a sequence detector, overlapping sequence detector, non-overlapping sequence detector, and etc. So maybe I'll try to take one example and try to explain in detail next week. Okay, so that would even give me some kind of learning. I would, do that. Any other questions? Any other questions? So, see, this whole subject you guys would have gone through a whole semester. At least you would have spent minimum 50 hours of time. Whereas I tried kind of, quick revision with the, kind of say 5 hours of time, 5 to 6 hours of time. uh, there is, obviously I might have not covered many things, but whatever that is necessary for you to be a PD engineer or any PD engineer should know, I have covered. And for your interview purpose also, some of the things I have covered it. So my, what I always suggest you is go back and open your textbook. See, you don't need to mug up any kind of theorems and equations. So just try to understand what is what and try to spend some time. Then you would definitely, have a clear understanding. But now let me tell you, this is the time that you have. You have a time now. You can go through it. The moment I'm telling you, after 2 weeks of time, whatever that I'm going to cover, you have never seen in the past. Okay, so you will. I've been telling this batch after batch. Finish your basics every, when you have a time. Okay, do not, keep it open. And the moment I'm telling you, the syllabus that what we have is literally vast. So you may not really have a time to just go through, or have, see, only these two topics are kind of basics. So once the moment I get into this here onwards, so PDK, technology library, standard cells, and macro libraries. So there are different models, lib, and what is CDL, and then what is Verilog model. And then I would have to, teach you complete SDC in and out. How do you write an SDC for a given design? And then I have to teach you the whole complete, the STA and all of that. So the moment I get into this other topics, I'm telling you, you have not seen it in the past. It would actually take lot of time for you to revise, so you will not be able to come back these two topics. Okay, so please go through it every day. My suggestion is, if you cannot afford at least minimum 1 to 2 hours every day, this course is not for you. I'm telling you, that is a reality. If you think, okay, you will just come only on Saturday, Sunday, you would try to, sit and do the things, or, only on Saturday, Sunday, it will not work. If you cannot afford 1 to 2 hours, I would strongly suggest you to drop from the course. So go and save your time. Later, you would just feel bad that, okay, you have done the course, but you did not learn anything. So this is my strong request. If you cannot afford to spend time 1 to 2 hours every day, um, please drop out the course. And if you have made a payment, I will refund you. I don't have a problem, but I need 1 to 2 hours of your time every day. Without that, I don't think you would be able to achieve what I wanted as a trainer, where I wanted to see you. That will not happen. So I'm telling you, you might look, see, we have a close to kind of how many modules? Around 34 modules. Now, to be honest, covering all these things in 20 weeks time is really, really challenging one. Okay, so I need your support. Without that, I won't be able to complete. So to be honest, right, to complete this, I would need minimum 1.5 month time. To complete this whole thing, I would need 1.5 month time. You guys might be thinking, why 1.5 month? What is the big deal, and etc. To enable you, and I would be giving you multiple lab assignments and slowly making you get exposed in Linux OS, and you will start looking at the tool and everything. And this is the part. So these two things I would just actually cover little later, and but all these things would actually take another 2 more months. So each topic, 1 to 2 weeks of time would definitely take, even if I try to be precise and perfect. Okay, then also it would take time. And let me tell you, your assignments are not, the real topics are yet to get started. So you are not seeing, I'm not giving you much of assignment, letting you just go and revise. But the moment I get started on the real topics, you would actually see a lot of assignments coming in your way. Okay, so you need to spend 1 or 2 hours, 1 to 2 hours of time every day. Without that, you cannot see the success here. I'm telling you. Okay, I think that's all for the day. I don't want to occupy you here. uh, I'm done. If you have questions, you can stay back and ask. If not, then you can drop off.
Hi, sir. Am I audible?
Yes, yes, you are.
Sir, since you mentioned that, and I was very curious to know this, why don't we use like T flops and other file that would be easy for the toggling purposes and all in the design?
See, it is, we always use only the D flop. So I think you are basically from standard cell background, if I'm not wrong, right?
Correct.
So
Right.
have you developed any kind of T flop as a part of your library development? No, right? You
No,
might
no.
have always developed only D and latch, and then SDFF, correct?
Correct.
So people always see, to be honest, right, I don't know why it is decided. So the moment when I was a standard cell designer, it was way back in 2004 and 5, I believe. So from that time, we have only SDFFs kind of, DFFs kind of being used in all the kind of designs. So that is what I would say. I'm not sure why they are not picking T. It is kind of, D would be kind of, the data flop. Maybe the tools would be able to do a better job if it is a D flop. That is what my understanding. But because when you do synthesis, right, so it would be easy if it is a D flop,
Yeah.
right? Yeah,
Yeah. From that point, yeah, it may be.
yeah, right.
Okay, thank you.
Okay, all right, guys. See you then. Take care. Bye.